In this lesson we will be studying complex series parallel networks. There can be a wide variety of complex series parallel networks. Each circuit must be inspected based on its particular characteristics and the various parameters such as total equivalent resistance, branch currents, voltage drops across individual resistors, and powers dissipated may then be calculated. Let's examine the complex series parallel circuit diagram shown. We will find the current in the circuit first. Finding solutions to complex circuits requires certain steps to be followed. The total equivalent resistance for the branches R6, R7, and R8 could be determined first. The equivalent resistance combination for R6, R7, and R8 will be designated as RT1. 1 divided by RT1 is equal to 1 divided by 120 plus 1 divided by 150 plus 1 divided by 180, or RT1 is equal to 48.6 ohms. The series combination R4 and R5 is in series with RT1. Hence, the total resistance for the combination with R4, R5, R6, R7, and R8 is 50 plus 250 plus 48.6. That is, RT2 is equal to 348.6. The equivalent resistance combination for R4, R5, R6, R7, and R8 will be designated as RT2. The series combination R2 plus R3 is parallel to RT2. The equivalent combination for R2 plus R3 and RT2 will be designated as RT3. Thus, RT3 is equal to the quantity R2 plus R3 times RT2 divided by R2 plus R3 plus RT2, which equals 200 plus 100 times 348.6 divided by 200 plus 100 plus 48.6, or 161.24 ohms. Finally, RT3 is in series with R1. Hence, total equivalent resistance for the circuit is equal to RT3 plus R1, or 161.24 plus 150, which equals 311.24 ohms. Current in the circuit can now be determined. I is equal to E divided by the total resistance, which is 18 volts divided by 311.24 ohms, or 0.058 amps, which is equal to 58 milliamps. Solving for the branch current I1, we use the equation I1 is equal to E minus V1 divided by R2 plus R3, which is equal to E minus the quantity I times R1 divided by quantity R2 plus R3, or 18 minus 58 times 10 to the minus third times 150 divided by 200 plus 100, or 0.031 amps, which is equal to 31 milliamps. We will now calculate the voltage drops V2 and V3 across R2 and R3. V2 is equal to I1 times R2, which is equal to 31 times 10 to the minus third times 200, or 6.2 volts. And V3 is equal to I1 times R3, which is equal to 31 times 10 to the minus third times 100, or 3.1 volts. To determine the voltage across V1, we use the equation V1 is equal to I times R1, or V1 is equal to 58 times 10 to the minus third times 150, or 8.7 volts. Checking, we know that E is equal to V1 plus V2 plus V3, or 8.7 plus 6.2 plus 3.1, which is equal to 18 volts. Last, to find the value of the branch current I2, we use I2 is equal to I minus I1, or 58 minus 31, which equals 27 milliamps.